So today we are starting new lecture, and it's going to be on Python and the fundamentals of Python programming. I have already uploaded this time on Canvas the PDF for this new lecture that I'm calling Lecture 2. So before I get going, I want to stress something that I said at the very beginning of the class, but Nigel wanted me to stress it again. Organize a folder called PGE310. In that folder, I want you to have a subfolder lectures where you can download all the lecture files. Okay? Code where you can download all the code just like I have it in Canvas. Okay? Homework. And then in that homework subfolder, every separate homework should have a subfolder homework 1, homework 2, and so forth. Okay? For your own sanity later this semester. Second part, that folder, maybe it's on your desktop, maybe it's not. The best practice should be to sign up for UTBox, Dropbox, or any other cloud type of service. There's UTBox available to you through UT. There are all other options there. They allow syncing. So all of my files are actually synced into Box. Okay? These are all of the folders and subfolders I'm currently working on. And the moment I'm online, they're syncing. Okay? And right now, actually, they're all synced. Otherwise, I have a little syncing sign on there. So if my cat eats my homework, right? If something happens to this computer, and you lose it, it starts working, somebody spills coffee on it, and so forth, the latest version of your file is on the cloud. Okay? So that way, and things will happen as you proceed in this semester. I mean, there will be, I can tell you statistically, 3 of you, I don't know who, but 3 of you will have computer issues, either lost or stolen or something happens to the hardware. Okay? So if you have things synced, you can actually show up and you can log into your account online and you can come to the computer lab here and continue working on the file. Second thing, speaking of cats and dogs eating homework, okay? If something happens and you didn't say upload your file to Canvas on time, okay? If I peek into that folder on your computer and I see a file that was last opened just before that homework was due, I know that you completed it. And you can submit that file, you can prove it either to me, you or myself during office hours, that you actually had that homework complete before the deadline, even though something happened in transit. Okay? So use this latest technology and things being constantly online to your advantage. Final thing, if you are submitting paper homework and you forgot to read that 3-pager of a frequently asked questions document that you uploaded, so you didn't staple your homework or whatever might have happened to your homework, take phone pictures of it. So if you're submitting something on paper, take a phone picture of it if it's handwritten for your own, and you can again, by the date on your phone, prove that you had it ready, done, and whatnot. And if one of those pages is lost in position, well, you have proof that you had it. Okay? So use the technology to your advantage. As long as we can unequivocally prove that you actually completed your homework before the due date, we're going to take it into account. Okay? So please use the technology. Anyway, lecture on technology over. Organize your files and hopefully, please put them on the cloud so you can access them at all times. That way, you can also sometimes leave your laptop at home and you still access those files when you go to the computer lab over here and continue working on whatever it is that you're working on. Okay, so that's just sort of good practice. All right. So now, as promised, let's start with our Python fundamentals. Yeah. So Python is just one of possible programming environments. It's called the language programming language that we use to communicate what it is that we want done, and often repeated 1,000 or a million times and so forth to the computer. So in that sense, the reason we could do this particular class in any programming language. This class for a long time was in MATLAB. Okay? If you ask any older faculty here, we have worked in C, C++, Fortran, and so forth. There are other programming languages. So it's something, what that points out, is it's something that changes. Okay? And you can, in your lifetime, expect that Python is popular now, but 10 years from now, it might be something else. Okay? So this will change, so you need to accept it, because languages in programming evolve, and they also evolve with available technology. So some languages are better at certain things than others, and that will change. Okay? So Python right now is very popular. It's because it's very close to the operating system and can move data around really quickly. It's also open source, meaning that there is everybody from all over the world contributing to it. That can give a little bit of headache, because there is no single company putting a lot of resources into making it pretty. There's multiple resources, and they sometimes don't agree. Okay? So when you actually type in Python help or something like that into Google, you're going to find too many resources, and sometimes it's hard to wind them down. Okay? We will show you one selection of the resources in this course that should be ample for your scientific or engineering purposes. Okay? It can work on a single computer. It can actually patch different codes from different other languages pretty efficiently. So it can also work in what we call high-performance computing, which is parallel computers. This is not just single machines, but multiple machines working together. So right now, it's pretty much omnipresent in industry. Okay? So I have the name itself. It's not directly from a snake, but it's from inspired by Python in 1970s Monty Python's Flying Circus. So we will have more, you will see Python 2 and Python 3 code available. We will work in 3. There are slight differences in syntax. Okay? So sometimes when you see a legacy code in Python 2, that might not work with your Python 3. So just be aware of that. Python 2, there's a lot of code that's what's called legacy. There's a lot of working code that is still working in Python 2. A lot of computers actually just come with Python 2 and not necessarily Python 3. But if you have listened to us, I asked you to install Anaconda distribution with Python 3. Okay. So that can, sometimes it's actually going to remove Python 2 from your system. That said, both of them could coexist on a system, that's not a problem. And there's numerous online courses. Python.org is just one source. So it's kind of really everywhere. If you want a single course that is separate from what we're going to go from the beginning onwards, but if you want a separate course that is somewhat complementary and just doing things in a different way, Code Academy has, I think, a 10-hour course that you kind of sit through, and you can also get a certificate. I want to also point out that now there's quite an explosion of online courses, and a lot of them you can take for free. However, if you want to put them either on your CV or on your LinkedIn webpage, okay, then you might need to pay $50, $60, $70 for the certificate. It might be worth it. Okay? So you consider yourself, if a certificate is worth it to you, to prove to an industry employer that you have actually taken the class. Of course, taking this class proves something as well. But if you want to extend that knowledge, you can extend it online. And if you pay a relatively small amount of dollars for those certificates, it might be worth it. Also, when you pay for something, you're more likely to complete it. So there's that's a good reason to pay a relatively small amount of dollars. So that's something for you to think about as we go through this course. If you want to extend your knowledge and add to your resume, these online code courses are definitely an option. Okay. All right. So you probably already have. I'm not gonna right now exemplify, but Python kind of exists and you can just run it from a command line. We're not going to do that right now. I'm just going to show you how to use a little more user-friendly environment. Okay. So everybody has everybody installed Anaconda? If you haven't, please say so. We do have help in class that can help you out. All right. So I'm assuming you have it. So let's open it up. So there's Anaconda Navigator somewhere that basically has. So this is basically an ensemble of tools that is very useful for sort of engineering/science applications. So technically, it should be everything that you need. Okay? That said, everything under the sun could be added to this as well, and there's a way to install additions. Actually, at the end of this course, if you put together all of the functions that we work on in this course, you could call that PGE310 plugin and create a code that installs it, and you can share it with other people and they can install those functions. Okay? So why do I want you to think about that? If you start building yourself a little software library, and I'd like you to do that as you're in this course and other courses. This is typically foundation for most others. So let's say that how many of you are in thermo? Excellent, most of you. So by the end of this course, I'd like you to have thermo.py, a collection of functions that you have put together while studying for your thermodynamics, okay? That can help you out and calculate things. And then after that, you're gonna go next semester. If you do transport phenomena next semester, you're likely to do the P. And guess what? It'd be really nice to have also transport.py and so forth. By the time you finish your degree here, you will also add petrophysics and geomechanics, information evaluation, so forth. You can have a little library of to-go-to tools that computes most of the things that you learn in this degree, and that could be something that's a tool that you carry with you. So think about it. Okay? Anyway, right now we will use from this two things. We're gonna use Spider, and we're gonna try it today. So I'm just gonna launch Spider. And we are also going to use Jupyter Notebooks. So those are most of the things that we're going to use from here. So Spider is starting. And while it's starting, I'm just going to, so I'll let it be in the background. We will get to it. So just start it up. And I just want to make a couple of more comments. So this is an introductory course. We're using Python as an accessory to learn something about numerical methods. You will not be an expert programmer by the end of the course. That requires practice, and kind of practice from now on, okay? Just like being fit. So, but it should be a great starting point to build on. But only really continued practice. And once you get to Dr. Bauhoff and reservoir simulation, what's the official name of the course? PGE?
3.3M.
There we go. Then you'll be able to claim expertise by the end of that course, right? Because you will spend actually applying things in reservoir engineering and building a more serious piece of code, okay? But it's a lifelong activity, really. Okay? So today we're going to start with fundamentals. Basically, how do we define things? Very basic things. How do I store and retrieve from memory all types of arrays that I might need? And then we will proceed basically with going through matrix operations that you've just done by hand, and you just handed in the homework. That same homework you're going to be redoing in Python basically within a week. And we will refer to some most commonly used built-in functions that kind of help us go beyond what we did in homework. So in your homework, you were playing with 3x3 matrices and 4x1 and 1x4 vectors, okay? That's small. That's not what we need. I haven't heard of a reservoir that is discretized into a 4 by 4 by 4 volume. Okay? That's a little too small. So we typically need millions and billions of numbers. And those millions and billions of numbers, we're not going to be manually typing in. Okay? We're going to have to find more effective ways to basically communicate that data and take it into our program, or spit it out, or share it with somebody else, and so forth. Okay? So that's what I actually mean by input-output. How do I do input-output of large arrays or any type of information? It could be written words and text that I want to communicate as well. And also, there's no good interpretation of the results without good visualization. And that kind of is hinted at the very beginning of this. I think I stole this picture from Dr. Valha. Okay? So this is a reservoir permeability field. Okay? And I have an injector and producer. It's three-dimensional data. Okay? That tells me immediately where the tight spots in red, or those more open that are in blue. That type of information, like, oh, you know, it seems that on top portion of this reservoir, most of the flooding will go to the open spots. Okay? That type of information is important, but I'm not going to gain it by looking at million numbers. I got to be able to plot them. Okay? And this type of visualization enables us to do so. We're going to have that exercise as homework. Okay. So let's get going. And we opened Spider already. For your information, I have already uploaded all of the documentation. This is actual code, and it's in your code subfolder on Canvas if you need to refer to it. That said, I'll be going slow enough that you'll be able to type things with me. So let's get started with playing in Spider. I will actually kind of not refer to... Oh, maybe not. Oh, maybe I will. Never mind. Oh, here is Spider. And it's asking me to update. I will do that later. So just quick orientation. Okay. So there is a code here, and that's something I'm going to turn off what I had before. So this is where I could just type in some code. Okay. This is what we call command line or console. And that's where results. I can type in directly into console. If I want to save work and refer to it later, then I want to somehow either keep typing here, and once I work out what I like and what works, then I transfer it to a file and save it as a file. And I can open and execute that file later. So you can always just type in things on the go. But most likely than not, you will want to repeat things and come back to them later, in which case you have to save them in some way. And we're going to be saving, if working in Spider, a direct piece of code that is in Python is typically .py. We're going to be working with .py, and we're also going to work with another type of Python file, which is not the same as .py. It's called .pynb notebook, which has a little bit of graphical input to it, and is actually, you can open it from web browsers. But because of that, it requires a different support. So those are two different file types, and they're not equivalent. But essentially, we will have our code in those two different ones. So let me just first try to type something. I can use Python as a calculator, though it's more powerful than a calculator. So I can just say 3 plus 4. So my in was 3 plus 4, and my out was 7. Well, we know that 3 plus 4 is 7. Nothing is saved right now. 3 is 3, 4 is 4, and it gave me the result. And I can't go back and grab either that input or output. It is variables, we call them variables, that basically reserve a location in computer memory where the numbers can be stored. So if I actually want to store number 3 to get back to it later, I will say a is equal to 3. Okay? Now it seems that there is no output. Well, there is no output. I didn't really ask Python to calculate anything. I just defined a variable named a that is equal to 3. Now I should have a variable explorer here. Okay? So you can immediately actually, so if you click on variable explorer, has everybody found it? It'll take you a week to kind of find your way around this. So give yourself time. Variable explorer tells me, I do have a variable a. Okay? It's an integer, int. Its size is 1. I have only one item there. And its value is 3. So I can quickly explore what type of variables I have. I could also define b as 4. And I will see that a plus b shows up. And I can do a plus b here. Maybe it's going to print it, maybe it's not. We're going to see. It will. I can also request it to print a plus b. That sometimes depends on different environments. So sometimes if your result doesn't show up for some reason, ask for printing. Print. I have immediately right now actually introduced one more type of object that is not a variable. This print. It apparently knew what to do when I typed in print. That does not come out of thin air. It's programmed behind. Okay? So it's actually what we refer to as a function. I gave that function input, a plus b. Plus is also a function, by the way. And it gave me the result, and it printed the result 7. Okay? So print is what we call a built-in function. You will, in this course, actually create a whole bunch of functions on your own that will be named however it is that you want to name them. This is the part of the standard Python package. Okay? So we can expect it to be loaded into anything that actually has Python with it. I can expect print to work. If you define the function, you can expect it to work only if you share that function file with people that you want to see that function. So that's just something to have in mind. So now, of course, I can do, so my result 7, is it stored in memory? Can I grab that 7 without typing it again? Who do I have? Variable Explorer. Do you see a 7 stored anywhere? So if you didn't tell the computer to store it, well, it's not stored. It's kind of fleeting information. It's printed here, but it's kind of gone. Okay? So that's something to have in mind. Computers do only what we tell them to. So you might think it's a good idea to store that number 7 because you might use it later. But if you didn't do so, computer will not know. They don't read minds. They have to be explicitly told what to do. So if you wanted to store this 7, we can define another variable, okay? And I'm just going to say c is equal to a plus b. And then my c, the moment I say equal to, I'm basically assigning the variable. And what's on the left side, okay, the result of this operation on the right side will be stored into a piece of memory that we named c. Okay? We can name it anything, but don't push that anything. Okay? The best is to use letters. Lowercase and uppercase are two different things. So if I actually say c with uppercase, a different variable will show up. Okay? So it's just like another name, like Chris sounds like Chris, but I could write it down in something like 5 different ways, right? Same thing here. But computer differentiates how do you write things down. So uppercase and lowercase is different. I could add numbers to my variable names. Just don't lead with a number. Even if programming environment allows it, it's kind of just not a good idea. Don't use special characters or not too much. Maybe just some underscores and some basic ones. Avoid a dot. Okay? But overall, at the beginning of your programming career, really, lowercase, uppercase, maybe some numbers at the end. Don't push too far. What I can't do is certainly use plus, because plus is already something that is an operation. So if I try to define a variable called a plus b, computer will be confused. Okay? Because it's going to try to execute that operation. That's what it's basically programmed to do. And then if you're trying to name a variable that has a plus in there, it's just going to get confusion ensues. Now, sometimes it still might do something without telling you, and those are the worst. Okay? When you think that you told computer to do one thing, computer actually has some other priorities the way it's set up and does it, but it doesn't give you an error. That's a problem. Okay? So basically, just stick with some regular names. So again, we can also have different types of variables. So all the numbers here are integers. Now, of course, integers are not the only numbers. So I might want to type in a D that is 7.4, say. Okay? And I need to give it a little more space here. And it has named it as float. Has anybody heard of this word here named float? Float, or floating point, it comes from floating point, is what computer scientists refer to as real numbers. And we're going to get to how do we represent real numbers in a computer. Okay? It has to ultimately somehow get translated to zeros and ones. Because really, the only thing the computer knows is on and off. Okay? So we have to somehow translate when you say A or 7.4, we have to figure out how to represent that with a string of zeros and ones. Okay? And tell computer. Now, for now, just know that float is a real type of number, so that's the one that has decimal point. Early on, the decimal point was referred to as a floating point. So float remains a name for a real number of the computer. Okay, so that one, and it seems that this computer is pretty smart. So it immediately knew that this number requires a different representation. It's not an integer, it's float. That's what's really nice about Python. There are some hardcore languages like C or C++. You have to tell it, I want a floating point number D, and then I assign D to be a floating point number. And that can be a pain, trust me, because you can't just type things in as you go. You have to declare what you want first. Get your bucket first, then go get water. Right? Here, the bucket is the source of water, so you just fill it in. Okay? So that's something for you to know if you go and learn a different language. You might need to declare everything up front before you actually move on, but there's a convenience here in Python, actually in MATLAB as well. Some of these programming environments, they kind of scope what they need to do, and they assign it immediately. Excellent. We can still do operations, so I can say, hey, print me a result of C minus D. What should I get? What is C? 7. What is D? 7.4. What is 7 minus 7.4? So that's what I should do. So learn to check the computer. Right? You expect minus 0.4, but that's if everything goes as you expected it to. So learn to double check. Okay? So this is a simple case where it's actually really simple to double check. What did it do? minus 0.4? Sort of. Close enough, eh? We're going to learn why this is the case here. This points to the fact that 7 and 7.4 are not stored in computer memory exactly, in part because our memory is finite, and we can't go with like infinite number of points. And also, they're not stored in decimal system. What we use is decimal system. 1, 2, 3, 4. My digits are 0 through 9. Digits for computers are not 0 through 9. They're 0 and 1. And there's a little bit of error that is made in translation. Okay? And that error is evident over there. So we're going to move on as close enough. This is actually the best we can do right now. But what's also nice of this computer is that it figured out, even though, as we will learn in our later lecture 4, I believe, that 7 and 7.4 have very different ways of how they're stored in memory. This computer was nice enough to figure that out and do the operation anyway. So it did a little bit of translating for us underneath. So our brains immediately say, well, what's the problem, 7 and 7.4? Except that there are different types of buckets that called integers and floats in computer memory. And if you can't do apples and oranges, even though they're both fruit, easily. Okay? But computer has figured this out behind, but that can sometimes be a source of error. So just again, computer is smart enough to do the operation anyway. Okay? It does point to some strange things happening in some very small portions of the number. We're going to get to that. Why is that? But that's basically a small error that happens between translating the number that we want to represent and the finite amount of memory that we have for actually representing it. Okay? All right. So one more thing is that numbers are numbers, but numbers are not all. I would like sometimes some text. Okay? Now, the way we can do text is I'm going to call it a message, and I'm going to keep it simple, hello. Okay? So this is now text, and the way I'm telling computer, hey, this is text, not a name of the variable, because if you notice, message is already a text. But some computer somehow knows that, hey, this is a variable called message. Okay? I'm going to give it special signal at the beginning and at the end that this indeed is supposed to be interpreted as text. Okay? And when I look at my variable explorer, there's something called str. We have already learned that computer science has weird names for things. Well, text is referred to as string, str, string. So I have size 1, as in I have one of them, even though the length of it could vary, and it's called hello. I can type in anything, really. I can call it anything. So I'm going to say question is, it's about noon, where is my lunch? Okay? So I can type in anything I'd like. It's not going to question me whether this text is correct. Okay? This computing environment will not. Your word processor might question your grammar here and there. These systems will not. They're not programmed to do so. Okay. And it's still going to say, oh, I have only one of them, right? It looks at it as some sort of array, and I have only one of those things in there. And its value is, where's my lunch? I can print that question just like I can print numbers. Okay? This print command is really smart. It can print numbers, it can print text, and so forth. And we are in a specific environment, Spider, that is designed to make things a little easier on us. So this variable explorer is something that comes with Spider. It doesn't come with every Python environment. So Python has a way to tell you what is the type of your variable. You can just say, hey, what is type of A? And it's going to tell you, hey, this is integer. Or what is type of your message? That is string. Okay. So this is if variable explorer does not exist in the environment you're using. Spider is only, again, one of them. Then you can explore what type is with the command type. So how many commands do you know by now? 10. Well, you know type. You know print. Those are the built-in functions. You know plus and minus. Sort of intuitively, what others do you know? If you know plus and minus, what other things probably work? Division, all of the arithmetic operations that you would expect to work in a calculator, yes, they work. So let's just try 7 divided by, well, 7.4. Has everybody tried? Have you tried percent? What happens with percent? Okay. So again, type is a function that just checks what type do you have. You can also use it to convert. So that 7.4, I could force it to be integer. Okay. I would just really say integer of 7.4 or 2.3. So give that a shot. Integer of D, or what did we call it? D, I think, 7.4. So in that process, it's going to round up the number, and it appears to just chop off whatever is after the dot. Okay? So that's something, again, to be aware of in any computing environment. Here's my spider. So if I say integer of 7.4, it's 7. Integer of 7.8 is 7. So this integer conversion, there's no one way to do it. Okay? This is what's called floor function in math, and that's what it seems to be doing. It's not rounding it, right? Because 7.8 should be rounded to 8. So I'm pointing another thing is that all of the functions that you're using, and sometimes you're using them blindly, they're programmed in a specific way, and they're maybe giving you the result you think they should be giving you, but maybe they're not. So learn to check and double check, and learn to basically go and take a look at what it is doing. What is it doing when it's, in this case, converting a real number to an integer. So again, this is basically this. Integer can be used as a function to force a number to be integer. Sometimes we have no idea. Right now I'm typing this in and I have no idea what's going to happen. I have some assumptions of what it could do, but I don't know how does it convert a string or text to, whoa, it doesn't. Okay? So it doesn't convert a text into number. Even though I actually know that every piece of text is a bunch of numbers behind, okay? But it's not going to do that by default unless it's programmed to do so. So you have seen your first error, okay? So whenever there's a bunch of things that you don't know how to interpret, that means you have an error. In this case, it tells you there's a value error. It's telling you invalid literal for integer command. It basically doesn't know what to do with hello. Okay? So computer will be most often very vocal about letting you know that it has a problem. Sometimes it's silently. It silently does something that is unknown to us, and that is an error, but it's not necessarily detected. Those are the worst. When you have an error, but you have no idea that you have it. And now before we move on, I said something about saving this code that we were typing here in for reference later. That's actually what I did, and well, what I did last year, and I uploaded it as your Python code. So it's slightly different than I always type in something else in class. So if I want to save this, okay, as something, I can say, hey, I can save all of it or just portion of it. So literally by cut, copy, paste, let me save something else, maybe C. I'm just going to do portions of it and definitions of A and B. So this is part of my work, and then I can say integer of D at the end. So if I want to save it, I press a little save button, or I go to File, Save As. And this, I hope, is that you created your folder, and you have a folder or a subfolder in your files where you will be dumping all of these scripts that we create. This is called a script. So I'm going to go to mine. Might take a moment to navigate there. Okay. So I'm going to go to lectures somewhere. I have my Python scripts in lectures. And I'm going to say variables. You can name it anything you'd like. For some reason, it wants me to repeat. Oh, I possibly have a file. Okay? I have an internal problem. Okay? And now I can actually execute this, and it's saved. So the way I execute it is that there's a little run file command, and when I click on that, it ran that. It just gave me a trace of what it's doing, and the only thing I asked it to print was that 7 integer D. But now it's safe. My work is safe. Otherwise, the moment I exit this environment, everything that I typed into the command line might be lost. Some of it is in the history, so it's going to retain some memory of what you did, but it's not guaranteed. Okay? So some of it I can get back to by basically if in my command line, if you go up, arrow up, you go to previous commands, down, up, down. It typically has certain number of things that it remembers, like last 1,000, but that changes, and it's not a sure way to save things. So the best is to save it in a file. All right. I see you on Monday.